Hey, welcome back to Algebra 2. Today we're going to talk about conditional probability. All right, so when we have I say a lot, I'm sorry about that. When we have a conditional probability, what that means is that the event occurring changes depending on another event occurring first. So we'll talk about what that means in a little while. With an example, it will help you solidify what we're talking about here. So we're going to revisit this two-way frequency table about going to college and not going to college, males and females. And we're going to use the same notation with M being male, F being female, C being going to college, and N being not going to college. So I want to keep this in my screen here. So a female, the probability of a female in A says probability of a female is 22 out of 52, which is my entire sample space, and the probability of going to college, which is right here, is 29 over 52. Not so bad. So going to college, given they are female. So this is the notation that we're going to be talking about in this lesson. So the probability of going to college, given that they're female. So let's start with drawing a Venn diagram, and then we'll start talking about it some more. So in this case, we know that females, how many females do we have? We know this whole circle is 22. We know this whole circle going to college is 29. Right? We just picked them from our numerators. And if we look at our two-way frequency table, what I'm interested in right now is right here. What's the intersection? How many females are going to college? Females going to college, 13. So I know that this number inside here is 13. So I have an overlap. So 22 minus 13 is 9, and 29 minus 13 is 16. So that gives me my actual numbers. So I have 9 here, 16 here, and 13 overlap. So now let's think about what this means. So when we're trying to figure out the probability of a college given female, this is going to equal the number of college and female divided by the number of females. All right, so if we do this, now it's the number of ands. So that's our 13, both college and female, divided by just number of females, which is 22. So that's how you find the probability of one event happening given another event happening. So in your denominator right here, it's always going to be whatever your second is right here, whatever the given. All right, so if we had thought about it the other way, where what's the probability of a female given that they're going to college, the only thing that would change is this number down here. Instead of going to being 13 divided by 22, it would be 13 divided by how many went to college, which would be 29. So we'll look at a couple of examples next. So this is basically what I was just talking about. Which is more likely, that a person picked at random will be going to college given they are male, which is this one right here, or that a person will be male given that they're going to college, which is this one. And you might think that they are the same, but they're really not. So remember what I just said, what this formula is. It's the probability of C and M, college and male, divided by the given, the probability of a male. And the difference between that one and this one on the right-hand side is the probability of college and male stays on top, divided by, now this time it's going to be the probability of college. So let's go back to our two-way frequency table and find out what the probability of college and male is. So college and male, there it is right there, 16. So then I need the number of men, number of male, So I need this number for my denominator for my first one, and the number of college, which is this one. So those are the three numbers that I need to calculate my probability down here. So we just said the probability of college and male is 16 over the probability of a male is 30. This one is going to be 16 divided by 29. Now, sometimes it's not easy to recognize which is the larger or smaller number. So that's where our calculator sometimes can come into play. So, because it's telling us which is more likely, one or the other. Show that calculations for both. It should say show the calculations for both. There's a typo there. All right, so if you recognize what these are equal to, 16 divided by 30, that did not work, is 0.5333. 16 divided by 29 is 0.5517. So you can see it's more likely that this one is true, male, given that they're going to college. All right, so your calculator can help you determine which is the larger fraction if you need some help with that. Okay, let's move on to exercise 3, which, by the way, is our last exercise. All right, so we can generalize this process to calculate these conditional probabilities based on counts and a way to calculate these probabilities based on other probabilities. So, the survey was taken to examine the relationship between hair color and eye color. This sounds familiar too. I think this is an old one. The chart below shows the proportion of people surveyed who fell into each category, blah, 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 blah. Find the probability the person picked had brown eyes given they had blonde hair. So remember what this means. It means we're going to find the probability of brown and blonde divided by the probability of blonde. So brown and blonde. Brown hair, I'm sorry, brown eyes, blonde hair, 0.10. Probability of just being blonde, right here, 0.35. Do the math in your calculator and you come out with 0.29. That was easy enough. Find the probability the person had red hair given they had green eyes. So probability of red hair and green eyes divided by what's given, which is the probability of green eyes. So this one is going to be, let's see, red and green. Red and green, red and green, 0.15. And what's the other one? Probability of just green, which is 0.25. So this one is going to be 0.15 divided by 0.25, which is going to be 0.60. Now we're going to start introducing a concept of whether or not something is dependent on something else. All right, we talked about this in class a little bit, and we talked about, does having red hair seem to have some dependence on having green eyes? How can you tell or quantify this dependence? All right, so compare having red hair given green eyes to just having red hair alone. So let's write that down. Let's compare red hair given green eyes to just having red hair. So the probability of red given green is equal to, we did that on top. Remember that? It's right here. Right here, red hair give 0.60. The probability of just red hair alone, I have to go back up to our frequency table here. just having red hair is 0.20 right there, right? Just having red hair, 0.20. So they're asking if these are dependent or independent. Well, they're independent if those numbers are exactly the same. But in this case, they're not exactly the same. Not only are they not exactly the same, they're 3 times more likely to have green eyes. I'm sorry, likely to have red hair if they have green eyes. All right, so this is, it's funny when people say this, they're not dependent, or then, I'm sorry, they're not independent. But I like to also say that they are dependent. Now, if these two numbers were the same, and I mean exactly the same, then that would show independence. All right. In this case, because they're different, in this case they're very different. It's actually 3 times as different. That shows dependency. One is dependent on the other. We're going to talk about that some more in our next lesson. At least I think we are. I'm just going to double check that right now. Yep, independent event is 11.4. So we will be talking about this some more. This is just a little bit of a hint of what's coming because I knew we did more of this. All right, so until next time, be kind to one another, make good choices every day, and we'll catch you on the flip side.